Please, why?
Hey everyone, we're gonna start now.
Just again to the topic. Hello, everyone. Good afternoon. We're going to get started on location. I'll be your session chair for this afternoon. We're going to be discussing observations of escaping primary atmospheres, and we have Parke Loyd, our invited speaker, to kick us off, talking about observational strategies for exoplanetary atmospheres, particularly.
Thank you so much. Everybody can hear me. I think I hear myself, so I think we're good. Cool. Yeah, let's kick off a round of observational talks. I thought that the organizers gave a great prompt. Leo showed it earlier to the invited speakers. That was, at least for this talk, was like, what observational strategies can we use to pull as much physics as we can out of the observations that we get? That led to this not so creative title. That's the great thing about an invited talk. You can not be very creative. People are still going to be there. But here's a better title. What's in a transit? Escape edition. So before we get into that, I just want to thank a bunch of people. Lots of folks have influenced the ideas you will see in this talk. Lots of them even came up with the ideas, and I'm just repeating them. Several teams here. In particular, I want to call out some of the escape modelers and observers I've worked with closely who have really influenced these ideas. Shreyas, Ruth, James, and Ethan. All the good ideas are theirs. All the bad ideas are mine. So I want to start with, how did we get here? Why are we all in this room today? It goes back to the very start of exoplanet observations with this 51 Pegasi B paper. And if you read that paper, they are thinking in that paper about like, why does this planet exist? You know, it's odd. We hadn't predicted hot Jupiters before that. And there's this line where they say, this thing should be pretty hot. We're worried that it's going to be beyond the gene's escape limit, that its gene's parameter equation might have a low value, just in case anybody's bland. Okay, so it might be in a hydrodynamic regime. And it didn't take very long after that for us to actually observe escape happening around an exoplanet. The first transit happened 5 years later. Only 3 years after that, that same planet, HD 209, which we've already heard about and seen this plot for already earlier today, was observed in Lyman alpha and seen to have a very deep transit in that hydrogen Lyman alpha line. The scales are not the same on these plots. The one on the right, that transit is about 10 times deeper than the one on the left. And you can only really get that if there is a hydrodynamic outflow. But after that, it was kind of interesting. Even though that observation came in so quickly, the additional observations of more planets came in quite slowly, and we had only a handful more over the next 15 years, basically, until JWST changed the picture in 2018 with a detection of a planet in helium. And it's a smaller signal than hydrogen Lyman alpha. You're seeing the difference between two adjacent bands, and then this band that covers helium 10830 in that top plot, and then the difference between those two plotted in the bottom. But it's a clear excess transit in helium. And the only reason it's actually not deeper is because it's just integrating over a pretty broad band past 100 angstroms because it's low resolution. And that opened the floodgates, because helium you can observe from the ground. Hydrogen Lyman alpha you have to observe from space with Hubble Space Telescope. It's the only thing that can do it right now. So since you can do this from the ground, it has other advantages as well. We have, in the last 7 years, accumulated several dozen more detections of atmospheric escape using this helium line. So now we can make plots like this that Zhang made in his 2024 paper, where you're seeing all the helium measurements at that time with the detections in blue and the upper limits in red. And also, we've just embarked on the first survey of atmospheric escape in Lyman alpha. This is the STELLA program. The acronym is actually pretty much what I just said, Survey of Transiting Exoplanets in Lyman alpha. Schreyer and I are co-PIing it. And it was just accepted last year. It's 625 HST orbits to devote to trying to observe Lyman alpha transits of planets, the biggest exoplanet program HST has ever done. We'll return to this plot, so you don't have to try to understand all these points just yet. OK, so that's what brings us here today. We're in this regime now where we're no longer stamp collecting transit observations. We're starting in on surveys. We're going to hear about several of them this afternoon. And we are also starting to get to deeper characterization of existing systems. So I wanted to lay some foundation for all the talks that we're going to have this afternoon by discussing what creates, or what do we see when we see an escape transit. So I'll start with the typical transit plot, just to remind the handful of solar system observers we have in the room that we are not getting very detailed observations of these planets. This is what the transit might look like in optical. If we were to look in helium, you might double the transit depth, potentially. That's a good rule of thumb. And then if we were to look in Lyman alpha, you'll see a much larger cloud, and you'll actually see tens of percent, even up to 50% transit depths, with the possibility that there might be total occultations out there possible. OK, so the way I want to do this for the next 10 minutes or so is build up a table comparing the two main observational probes we have of exoplanet atmospheric escape currently in use. The two that I've already mentioned, hydrogen Lyman alpha in the UV at 1215 angstroms, and helium in the infrared at 10830 angstroms. We've already talked about one really key difference between these two is that helium you can get from the ground. So it's, in that sense, a lot easier to observe. Also, you saw graphically, I didn't explain why, that the transit absorption depths are pretty different for these two probes. Lyman alpha transits tend to be deeper, helium transits tend to be shallower. So let's now get into the details and maybe even answer that question of why the helium transits aren't quite as deep. Here's just my cartoon of the two versions. I know that the color scale is not great for the helium because you're seeing red on orange, but smaller transit. And for Lyman alpha, what you are seeing is absorption that results from this photon moving an electron from the ground state to the first excited state. It's pretty simple, and that electron will actually pretty much immediately decay back down radially to the ground state, but the photon will be scattered off some random direction, so we won't see it anymore. It'll effectively absorb the Lyman alpha. For helium, what happens when you hit it with a 10830 angstrom photon, roughly, approximately, is you don't actually make an electron jump energy states, not the full energy state. Instead, you're just changing, basically moving it from an s orbital to a p orbital to slightly higher energy, hence the infrared photon. You don't need as much energy to make this transition. And it's a little complicated because you need one of those electrons to already be in the excited state to begin with, in the first excited state of the atom. That's what that asterisk represents after the helium, is to indicate that we're looking at this atom in an excited state. But that means that somehow, in order to see this observation, this transit, we need to have a significant population of the atom in that state. And I am not a helium observer, so please take all the things I say about helium with a grain of salt, and somebody can correct me in the comment section if I get anything wrong. But based on reading the literature so far, it seems like kind of one of the predominant ways to excite this state is not necessarily to collisionally excite it, although you can, but you can also collisionally de-excite it. It's to hit it with an XUV photon. And then you will ionize that ground state helium. And now that ion has the opportunity to grab an electron from whatever electrons are around in the fluid. And when it does, it has a high probability of recombining into that excited state. So this is how you can get a significant population of excited helium. It's a little more complicated than that. I am simplifying things. Hopefully we'll learn a little bit more about it from Matthias and maybe some of the other talks later. But we don't have a whole lot of time for this talk, so I'll leave it there. So that actually kind of already brings up one point, which is that you at least want enough density that you can recombine pretty quickly when you ionize this helium. That's part of, or probably not the entire explanation for why you're generally probing a smaller transit, because you're probing denser gas closer to the planet. For Lyman alpha, it doesn't matter so much what the density is. It does. For all of the things I put up here, I should mention there are exceptions and nuances and all sorts of stuff. So these are all rules of thumb. And then we also talked about an XUV photon. They're exciting that helium, or ionizing it so that it can then recombine into an excited state. So in the case of helium, having a higher ionization can actually potentially be beneficial to populating the state. To fill in that empty column for Lyman alpha, I'm going to get into a key observational detail about Lyman alpha. So hang tight for a sec before we fill it in. Let's go back to this plot from that first atmospheric escape discovery paper from an exoplanet for HD 209. This is flux as a function of time, but you can also look at both Lyman alpha and the helium data as flux as a function of wavelength and plot up the spectra. So this is what that one looks like. I'm worried I'm standing in front of my slides too much. If you were to look at the spectrum, you have in transit as the solid, the bolder line, and outer transit is the skinnier line. And you'll see that it looks like two lines are there. There are not really two lines. The star has effectively just a single line, Lyman alpha. Probably looks like something like that blue curve. But there's a bunch of hydrogen in between us and the star that we're looking at, which absorbs the core of the line. So that's why it looks like two lines. This means that if we are going to observe a hydrogen transit in Lyman alpha, that hydrogen needs to be kicked one way or the other along our line of sight so that it gets Doppler shifted into one of those two wings. Here that is, again, basically just in cartoon form. If we could image the Lyman alpha, that gas that you see occulting the star, it needs to be moving towards us for the absorption to get pushed into that blue wing of Lyman alpha line. One way you can do that is by pushing it with a stellar wind. There also might be regions of parameter space where radiation pressure could do it, or you could have charge exchange that's producing a similar signature but without actually pushing the wind. I'm going to focus on stellar wind pushing today. And if we were to look at that system from above, we might see something like this, where the wind is pushing the tail so that it gets that kick that we need to see it in the line. OK. So that then allows me to add a row for the typical RV range where we can observe this. For Lyman alpha, you generally need stuff that's beyond about 20 kilometers a second from the core of the line. And then that goes back actually to this XUV conditions. If you're looking at stuff that's been accelerated by the environment that it's in, it generally has to get further from the planet for that to happen. So we're generally probing lower density material. And that means that if you kick this electron out with an XUV photon, it's not generally likely to come back. So that's bad for observing Lyman alpha because you need that electron in that state in order to absorb a photon. So we actually don't really want a whole lot of ionizing flux for hydrogen. Again, there's nuances. The amount of ionizing flux you're getting is also changing how much mass you're losing. But practically, it seems like this is the trend. Now, let's go for that last cell next to helium. Helium, you don't have this problem with the interstellar medium absorbing the stuff that you want to observe. These are the helium lines. This is the first spectrally resolved detection. And there is, however, a bit of a practical constraint because you do have some telluric features that are near this line. And because they're telluric, they actually move around depending on when you observe the planet, because Earth is moving at 30 kilometers a second around the sun, so it can get a little tricky observationally. So I will put in that column, say we in general can observe stuff fairly well, less than 30 kilometers a second. The observers in the audience might have a different number in mind, but hopefully that's a decent rule of thumb. We can get the core. That's the key thing that you want to remember about helium. And this then translates into how powerful these are for constraining mass loss, actually. Because that hydrogen, because it has to get kicked by something for us to see it, that's one step removed now from when it escapes the planet. And so you can generally get more powerful constraints on the actual mass loss rate with helium than you can with Lyman alpha currently. Again, exceptions probably to all these rules. If you want to see a case of this, actually go check out Stella's recent postdoc hire, Eva Morrissey's poster. OK, hopefully that lays some foundation for kind of understanding what we're observing with these two different probes and what influences those observations, which then sets us up not just for the next round of talks, I hope, but also to discuss what are some strategies that we can use to probe these planets. Now I'll show you this plot again. So the first strategy is actually as obvious as the nose on your face, right? We just need to detect these things if we want to probe their physics. And non-detections, they are also wonderful. And I am super happy that people have been really good, I think, recently about publishing non-detections in our field. And those can be used to test whether our models are predicting the right things or not in the right places. But if we want to then dive into the deeper details, we do need some detections of these planets. And you can see on this plot, this was at the proposal stage for Stella, plotting up an example sample for us. And our sample is the stars. We're plotted against the known planets as the background, as the blue shading and the little dots. And we've also plotted at this time known detections and non-detections. Those are the X's and the check marks. Don't worry about whether an X is circled or not. But you can see that the detections are they are outnumbered by the non-detections about 2 to 1. So it would be nice if we could get to maybe the opposite of that and say. And we have a strategy for this with Stella. It's actually very similar to the Rocky Worlds DDT. We're using checkpoints. That's what these different colors of stars are showing you. We're first starting with a broad survey to sample Lyman alpha lines, and then we're down selecting for transits, and then we're down selecting again for characterization. Here's why we're doing this first checkpoint. If you go and try to predict Lyman alpha line of a star, you might get things like these orange curves for 2 examples here. You can see that the optimistic and pessimistic cases are pretty different, the high orange line versus the low orange line. And then the observations in blue, in one of these cases, you're right by the optimistic prediction. In the other case, there's almost nothing. So by doing this step with with Stella, we can identify the lemons in our sample and kick them out before we do the next down selection. And then, so we're about 70% complete with this at the moment. We've got about 80 of these. It's a huge sample of Lyman alpha reconnaissance, and it's getting even bigger. And now we're starting to select which ones we are going to observe for transit. To do this, we're using a model made by Ethan Schreyer that effectively does what I showed in cartoon. So you assume an outflow from the planet, you push that outflow with the stellar wind, you do the radiative transfer, and see what kind of absorption you get in the Lyman alpha line. But a lot of the parameters of the system are pretty uncertain. So it's complicated to predict whether a transit will be detectable in Lyman alpha, and I'm sure the same is true for helium. So we're actually doing this where we map across the parameter space. So we vary the mass loss efficiency. We heard about that parameter a bit this morning. We vary the XUV flux, which we also don't have a great handle on. And we vary the stellar wind strength, which is even less well constrained, across a range of plausible parameters, estimate the signal to noise, and then we can rank our planets based on what fraction of that parameter space they would be detectable in. So hopefully this will increase our number of detections in Lyman alpha in particular, so we can actually start to probe the physics more of these planets, of their outflows. Also, even just detecting the outflow from a planet already tells you something about it. And I want to make that point real quick with the TOI 776 data. So we heard about high metallicity outflows earlier today. This is my rudimentary observer understanding of how metallicity influences your outflow. Basically, if you add heavy stuff, you're weighing down the flow, right? Some of the energy is going into the heavy stuff, lifting it out instead of lifting the hydrogen that we're going to observe. You're bogging down the flow. So those heavy species, their thermal velocities are slower. So you have a slower sound speed, so you have slower launching velocity. You're not getting the stuff out as far. And then they cool down the flow. This is what we heard a lot about this morning. You have lines, more lines if you have more stuff with which you can radiate away, dump that energy before it can go into lifting stuff out of the gravitational well. So for the Lyman alpha transit of TOI 776, which we published earlier this year, we used Ethan's model to basically think about where you could have a plausible hydrogen signature if you applied two of those three things. The fact that the oxygen is weighing down the flow and it's slowing down the flow. And you get a constraint. So this is a potential water world. So we were curious about what if you had a steam atmosphere. And on this plot, we're showing escape speeds that the model allows in that blue posterior region versus oxygen mixing ratio. So once you get all the way to the right side of the plot, you're looking at fully dissociated steam. And you can see that the model struggles to fit it once you get out to a steam atmosphere and without moving to unphysically high outflow velocities. So even just seeing escape, already we're probing physics that's happening there. Now, if we want to go deeper, there's kind of three axes that we can leverage to do so. One's wavelength, the other is time, and the third is kind of a meta-axis population. So I set us up pretty well, I think, for talking about population first here, because there is a trick we can use that's enabled by the fact that Lyman alpha and helium seem to be probing kind of different XUV regimes. Lower XUV for Lyman alpha, higher XUV for helium. So that means that we can build a bit of a ladder in outflows where we can observe the lower XUV end with Lyman alpha, the higher XUV with helium, and they actually overlap, which is wonderful. There are 3 planets now. There might be more, but 3 that I'm aware of where both have been observed for a planet. So we can cross-calibrate in that middle region and then use that to increase our confidence as we extrapolate out to either side. And this parameter, the XUV flux at the planet, it correlates with other stuff that we might be interested in the system and want to test our models across, like planet age and orbital distance and stellar effective temperature. Okay. So I think that's going to be a really powerful tool going forward, especially as we complete the Stella survey in the context of the ongoing helium surveys that are happening. We can also probe wavelength, and helium is helpful here because we don't have the core absorbed. So the width of the helium line is a probe of the outflow temperature. There are other things influencing the width as well, but that's one of the key ones. If you don't resolve the helium line at all, and you try to fit the mass loss rate, you see plots like this where you get a degeneracy between the mass loss rate and the temperature that's assumed for an isothermal outflow on the x-axis. Ignore the stuff that's going on in the middle there for now. Just focus on the blue line showing you this degeneracy between those 2 parameters. Dion Linson showed us that you can actually do one better. You can, if you put a physical prior on the plausible range of temperatures for the atmosphere of the planet, then you can break that degeneracy and confine your posterior a little smaller. What's even better from an observer standpoint, I would say, is to resolve the line. And then you get a better constraint on temperature directly from the observations and a smaller posterior. This is like amazing if we could do this with hydrogen, quarter dex uncertainty on the mass loss rate. Okay, what about time? If we mix time with a Lyman alpha transit, we can basically probe through the duration of this transit the speed of the outflow. So if I go back to this diagram where we're looking at it from the top, the ultimate thing that determines when this outflow becomes no longer observable is when it becomes ionized. Once it becomes ionized, we can't see it anymore. It's not absorbing Lyman alpha photons. So the faster that stuff is leaving the planet, the faster it'll travel down the trail, and the farther it will get before it gets ionized. So when you measure the transit duration, you're probing effectively how fast the outflow is leaving the planet and how fast it's getting ionized. There are nuances here also. To really do this well, we probably need a population sample to average over some of the key uncertainties, like uncertainty in ionizing flux. But it could be a way that we could probe the mechanism that's launching the outflow. So like, for example, core-powered mass loss and an XUV-driven outflow will predict different velocities, launching velocities. OK. I think I am doing slightly better on time than I anticipated. So I'll talk about one last one that I was considering skipping. But even better than doing just time or wavelength is to do them both. And I am interested in the possibility, and I think we're going to hear some about this, potentially from Romain later in this session, of observing the time-dependent wavelength structure of the absorption of the planet, because that could tell us how it's interacting with its environment, where it's getting accelerated and when. So Morgan McLeod made these plots from a simulation, 3 simulations that you see at the top there with different stellar wind strengths. So with a weak wind, we've seen plots like this already today some. Weak wind, the stuff can form a torus potentially. As you go to stronger winds, you get more of the cometary tail type structure that I've been showing in my cartoons. And that results in different signatures if you look at the absorption as a function of wavelength and time in these like streak diagrams that you see here. The signals aren't huge. We're looking at log excess absorption on the y-axis. But I'm hopeful that this will be because the stars are so bright at helium that we'll be able to get the signal to noise to do this. OK, I want to now think a little bit bigger beyond just how can we use the existing data to probe atmospheric escape physics better? What about getting more different data with new instruments? There's 2 key limitations I want to highlight that I think new observatories could help address. One is that we don't have a great handle on the ionizing flux. The last telescope to observe in the EUV ended decades ago, only observed a handful of stars. So it would be great to launch something where we could begin to observe this stuff again. I think we'll hear more from Kevin about this later in the week. There is a mission concept out there to do it. Similarly, going back to this plot, the modelers have been warning us observers for quite some time that there might be early ingresses for these planets. So if you look, for example, in the middle plot there's stuff leading out ahead of the planet in this sort of intermediate wind strength model. And the thing is, with most of our transit observations, especially with the Hubble Space Telescope, we get like 1 or 2 hours before the optical transit starts, and then a few more hours after that. But it's entirely possible that we are just observing a transit the whole time. And so it would be really nice to have longer baselines to figure out whether that's the case or not. There's another issue, and that's the star itself. So what you're seeing here, and I wish I could have figured out a way to speed up the frame rate because it looks way more dramatic. What you're seeing here is what the sun looked like on Saturday in the helium 304 angstrom line. So this is an activity-generated line, just like Lyman alpha and helium 10830 are also activity-generated lines. And you can see all sorts of like little stuff moving around the surface. You see these little blips where there's like jets and little flares that go off. Basically, these stars are not steady. And again, we're limited by our baselines here, especially with the Hubble Space Telescope. We just can't sample the timescales that we need to sample to get a good constraint on the stellar variability at the same time that we make a transit observation. So this could also potentially be solved with a dedicated observatory where we could observe these things for effectively as long as we want. And there was a concept that I was a part of, Evgenia Shkolnik PI'd, called UV scope that would do that kind of thing. And I hope to see it reproposed and be a part of reproposing potentially. Okay, and now I want to spend the remainder of the talk basically trying to put things back into context. I was torn between whether starting with history or starting with context kind of for this talk, and I went the history route because I find it interesting. But now let's put it in some greater context. So actually, Ruth really set me up well for this point about atmospheric escape regimes. If you look back at this 51 peg paper and you read the next sentence after the one that I first highlighted, it points out that basically non-thermal mass loss might also be a thing and important. It's actually, I would disagree with that statement for this particular planet, but it is nonetheless, it's been on our minds from the start. So I should add one final line to this comparison table, which is that for both of these observational probes currently, we're only probing one kind of atmospheric escape, hydrodynamic thermal escape. Ruth got me interested earlier in the fact that there are other collisional regimes that maybe actually could be a little more observable than I had previously appreciated, I think. But effectively, this is what we're limited to at the moment. And there's all sorts of other stuff going on. We know from the solar system. I think we'll hear more about this later in the week as well. We're only getting this one. But here is how Guillaume Gronoff decided to characterize all the others in that 2020 review paper. There's a lot of stuff potentially happening, especially for rocky planets. One of the key things that this brings up in my mind also is that these other escape mechanisms, many of which are non-thermal, are heavily influenced by the particle environment around the star. If you were at Know Thy Star 2, you'll know this is the corpuscular environment. Things like stellar wind and coronal mass ejections have an impact on these other types of escape. They also have an impact, albeit maybe a little smaller, on the hydrodynamic escape, and especially our observations of hydrodynamic escape, which was what you saw in that cartoon where the wind's pushing the tail, right? So the wind, this particle-based space weather, is having an effect on our observations. So going forward, we need to figure out ways to better constrain these. And several people in the room and I participated in this workshop. Jane and I and Joe Lazio and Greg Hallinan led it at the Keck Institute for Space Sciences workshop to think about this problem. We just wrote a report with some of our findings, some ideas, a lot of background on how this stuff works, and it is online. You can go have a read if you like. It will hit archive tonight. Okay, now let's think about bigger picture in terms of planetary population. So we want to observationally, basically, I would say, test our models to be sure that we're getting it right when we think about how escape is modifying the exoplanetary population and doing things like carving the radius valley that is so well known now. Also, we're now starting to think more about the cosmic shoreline, which, if I were to put it on this plot, would be a little bit below, because the radius valley is separating planets that have thick hydrogen-helium atmospheres from those that lost those and maybe have still a thin, geometrically thin, but still mass-wise significant secondary atmosphere, like oxygen and carbon-rich things. Different things have been proposed for what might cause a cosmic shoreline. Could be more these non-thermal processes, could be hydrodynamic escape early on is more important. And so for all of these, hydrodynamic escape, continuing to observe it is going to be key. Oh, right, this is where the planets fall. Mars, I learned earlier, should be right on the cosmic shoreline. I often say Mars doesn't have an atmosphere, to the ire of my wife who studies Mars's atmosphere. All right, so I'll end on a hopeful last note, which is, HWO will be here in a couple of decades, I hope. And Leo showed us that with HWO, we might be able to actually start to tease out the signal of hydrogen Lyman alpha absorption from rocky planets like Earth. So it's small. In this plot, it's just the difference between those green points and the blue curve. You can see that difference plotted at the bottom, but if you stack some transits, you can get it. And I'm hopeful that if we can get into that regime, that we might actually observationally be able to start probing things beyond hydrodynamic escape happening at these planets. I know there's a lot of complications that are going to go into that, but that's my inspirational thought. So I'm excited for an awesome round of talks this afternoon to dive into the observations with you all. I thought I would end with this beautiful image. I think I might actually do better for the question session by showing you that comparison table again, and hit me with your questions.
Great talk. Questions?
Okay, so I'm really intrigued by what? Dave Charbonneau at Harvard. Thanks, Eric. So I'm very intrigued by interpreting the width of the helium line. And in many of the papers I've read, the width is actually very close to the spectral resolution of the instrument. And so I wanted to get your kind of just view on, are there a number of detections where it's multiple times the spectral resolution? There's really no doubt the light's been resolved. And then I was wondering, must we interpret that as temperature of the gas? Could that not just be the escape velocity? It's, so the point is, if you have an isotopic escaping gas, could it not be that there's cold gas, and a major contribution to the line width is actually the velocity structure of that escaping gas and dynamical effects, and not actual thermal width?
Yeah, thank you for those questions. Should I repeat things for online folks?
No, there's ceiling live.
Ah, wonderful. Okay. So your second question, I will answer. Well, actually, I can answer the first one the quickest because I'm not a helium observer. I can't answer it definitively, so I don't know how many positive detections of a width beyond the the instrumental width of the line there are. I earlier had actually put a label that said thermal or outflow speed as like driving the width. And we also heard earlier about the 189 anomaly, effectively, where there's a line that's wider than the models would predict it to be. So it definitely is a lot more complicated, and I think I just betrayed my simplified understanding as a non-helium observer when I put that up. But as for probing different velocity structures, I mean, that is exactly what I would hope that we could do. I just don't know if it has been done yet.
That information would all be lost if we know it's dominated by some incredible temperature. But if we don't know that for sure, then it would be worth exploring, because you could do a lot of wonderful things with the velocity structure.
Yeah, absolutely. Like directly probing just moving cold gas, like you're saying. Yeah.
Thank you.
Sure.
Hi, Kevin France, University of Colorado. Thanks, Parke. Great talk. I wanted to ask about the handful of metal escape measurements that are sort of non-hydrogen and helium. There's a nice magnesium ion plot over there. There's some iron detections, right? It's like a half a dozen. It's not very many right now. But I guess I want to ask you, should we be investing in more of that? Because it seems like maybe we just haven't tried hard enough for metal absorption, or other things that you think would be useful about having species beyond hydrogen and helium.
Yeah, thank you for the question, because actually I was torn when I made this talk about whether to add a slide or two on metal lines. So just like you say, like we have several detections of absorption in metal lines that are part of the outflow in these escaping atmospheres. And I definitely think that it's worth it to continue investing in those. I don't think we've exhausted what is possible with the observations or with the tools we have currently to observe. I'm especially curious for smaller planets, like things like potential water worlds. Can we put constraints with oxygen on how much oxygen is in the outflow more directly than what I showed for TOI 776? And another point that brings up is that this is another area where HWO will clean up. I think I've seen also in Leo's paper a plot of carbon-2 for a GJ436, which unfortunately I don't have in this plot, but you can maybe really start to constrain them a lot better in the future. But to go back to your original point, yeah, I think we still have a lot to do there with our current tools.
Hi, Parke. Great talk.
Kaylee Rockcliffe, UMBC. I was just wondering if you wanted to speak to the power of simultaneous transits, maybe with like helium, Lyman alpha, H alpha, metals even.
Yeah, one of the things that I think would be really helpful with those, so I definitely think they should be done. It's basically like doing that population plot that I showed, but the same planet at the same time to really cross-calibrate those models well. Because there could be all sorts of variability that's happening. Sort of like HD 189's outflow is known to be variable, so you would get rid of that aspect of uncertainty. And then I think that because helium can give us tighter constraints on mass loss, if we combine the two of them, we can end up, we'll certainly break some or at least mitigate some degeneracies. And what I'm thinking about in particular is probably better constrain things like the stellar wind, ram pressure, if we have a nice constraint on the mass loss rate from helium to begin with. So I think the two together will be a great duo.
Katie.
Thanks, Park. This is Katie Bennett from Johns Hopkins. With the idea of with resolving the line to break that degeneracy between the mass loss rate and the temperature, what can you do in all the cases of those non-detections? Is there a way to, presumably you only interpret the non-detection patterns of the detections if we don't know what's driving the non-detection? We don't have a way of breaking that degeneracy. What do you do?
Yeah, I mean, it's a great point to make, and I don't know if I have any revolutionary ideas for for better interpreting the non-detections. To elaborate on your point a little bit, you could have a non-detection because there's not escape happening. You could have a non-detection because it gets ionized too fast, that we've seen several of those recently. You could have a non-detection because the stellar wind isn't pushing it enough, or it's pushing it too much. So the only way we'll be able to really break those is to get better constraints on the things we can potentially constrain. So like ionizing flux, better reconstructions, or at least like having a good reconstruction for the system, like having a nice X-ray and far ultraviolet spectrum you can use to get a good reconstruction of the XUV part would help with the ionizing flux side. And then things like constraints on the stellar wind, if we could figure out a way to do that without using the planet itself as the wind constraint, would be wonderful.
Eric Idos, University of Hawaii. So I enjoyed your review talk. You brought up the stellar variability in the sort of the bad sense that basically this is something that basically can generate false positives or limit our detection of these things. But isn't there another way of looking at that? And that is use the stellar variability itself as a probe for what's going on. So stars have magnetic cycles. The X-ray luminosity of the sun varies by a factor of 6 or so between maximum and minimum. And if we could actually observe these transits at different epochs, couldn't we use that to figure out what's going on?
I think that's a great idea. It reminds me of something that I didn't bring up, which is multi-planet systems are kind of the same as, everything is the same, except that the planets themselves are going to have different properties. But that at least like you've got the right absolute calibration for your XUV flux, and it's just the relative change between the planets. And this sounds like maybe even one better, because you have the same planet, but different XUV conditions at a different part in the activity cycle. That's a great point. You can always flip, I feel like, these problems into opportunities, and you've just done exactly that. I don't think I have more to add other than that would be wonderful.
Requires patience.
Yeah, exactly. Yeah, and you have to probably know the cycle, which we know for a fair number of stars now. So you could even potentially use the rotation of the star, but I think that would maybe be less reliable, I guess. You might not get as much variation either.
Let's thank our speaker again.
Surprised that one.
The little button right on top of it.
All right, up next we have Michael Zhang from University of Chicago talking about escaping helium from young mini Neptunes in the southern hemisphere.
Hello. Great. Well, thank you to everyone for coming. Thank you to Parke Loyd for introducing the escaping helium technique so that I don't have to, and I can jump right into the topic. The topic is mini Neptunes. So what are the mini Neptunes? Short answer is we don't really know. Long answer is there are lots of possible interior structure models that all give you the low densities that we observe. For example, maybe there are gas dwarfs. So there's a rock, and on top of it, there's a hydrogen-helium envelope that's maybe 1% of the mass that puffs up the radius. Alternatively, maybe the volatile layer that gives you the low density isn't hydrogen-helium, but a deep water ocean that's hundreds or thousands of kilometers thick. Now, we think that no matter what the volatiles are, over the course of the planetary lifetime, billions of years, a lot of these mini Neptunes lose their volatiles and become the smaller and denser super Earths. And that's what gives you the radius valley. Now, surprisingly, in the JWST era, our view of mini Neptunes has become more nuanced. Here are the 3 more models, right? Plausible interior structure models of mini Neptunes. Yeah, it's complicated. But we can use the helium line to test some of these models. For example, if you see escaping helium, you know that you can't be looking at just the water world, because otherwise, where's the helium coming from? If you see escaping helium, you can also probe this mechanism that strips off the atmosphere. Is it photoevaporation? Is it core power mass loss? Those give you different signals. You can even test some of these nuanced models by constraining the metallicity of the atmosphere. If you have a very high metallicity envelope that suppresses the helium signal very significantly, very dramatically. And so looking at the size of the helium signal gives you an idea of the metallicity. So to get all of these things, I started an off-sky survey of young mini Neptunes orbiting K-dwarfs. Why K-dwarfs? Because there's an old paper by Antonia Klefsich in 2019, which is old by the standards of escaping helium. Yes, and this paper said that K-dwarfs maximize the metastable helium population in the outflow. Now, there are some more recent papers that dispute this, but I started this survey a long time ago. Okay, so why young planets? Because that's the era when escape is the most vigorous and the most detectable. Now, I also chose bright stars because why would you not? From the northern hemisphere, I'm using NIRSpec. From the southern hemisphere, I'm using WIRED. These are both high-resolution spectrographs on fairly big telescopes. Here are the first 4 signals, first 4 observations from the north. You can see that these 4 detections are fairly similar. They're all around 1% if you take the in-transit average absorption. And from these first 4 detections, we can already come to some conclusions. For example, do these planets have primordial atmospheres? The answer is yes, at least they need to have some primordial atmosphere because we see helium, and helium cannot be dissolved in the interior. Now, I say that, but I know there's a recent paper by Akash Gupta from 2 weeks ago that says the opposite. So we need to revisit this first conclusion. Okay, the mass loss mechanism is very consistent with photoevaporation. We know this because of the width of the helium absorption. It's fairly broad. It's consistent with an outflow at several thousand Kelvin. That is very typical of photoevaporation and not very typical of core power mass loss. The mass loss rate. Well, we can estimate this order of magnitude, and it's enough to strip the atmosphere in a few billion years. So a lot of these planets could plausibly become super Earths. Lastly, the metallicity. If you run a 1D self-consistent radiation hydrodynamic model for these planets, you find that at solar metallicity, you predict a helium signal that's way too big. At 300 times solar metallicity, you predict a helium signal that's way too small. And at 100 times, it's just about right, just about matches the observations. Incidentally, that's about the metallicity that the JWST transmission spectra of the existing mini Neptunes has indicated. So I think it's at least approximately right. Okay, so that's the northern hemisphere. How about the southern hemisphere targets? Do they look anything like the ones I've already published? Well, for two of them, the answer seems to be yes. So here you see TUI 1027b and 2540b. They have transit absorptions of around 1%. Yeah, very normal looking. But then you get TUI 179b. First of all, even in the bulk properties, this planet is really weird. 2.6 Earth radii, 24 Earth masses, with an eccentricity of 0.34. Now, this is supposed to be a mini Neptune, but the density is higher than that of the Earth. So I asked my friend, Madison Brady, who's an expert on RVs, to refit the RVs. And what she finds is that the eccentricity is actually not that inconsistent with 0. And if you force the eccentricity to be 0, then the mass goes down to 12 plus or minus 6 Earth masses. And I think that's much more consistent with what we know about mini Neptunes. So if I were a betting man, that's what I would bet on. Okay, what does the helium signal look like? Well, first visit, beautiful helium signal. It's about 1%. We see a secondary peak. It's slightly redshifted relative to the stellar line. Second visit, we see nothing. And third visit, we see absolutely nothing to even greater precision. Several years ago, if you asked me what was going on, I would have said stellar activity. Like we're seeing stellar activity in the first visit. But since then, I'm not so sure. First of all, because I've actually looked at this star 2 more times, like way out of transit, and I don't see any stellar activity that looks like this. And also, we've done more and more helium transits as a community, and we have seen other apparently episodic outflows. There's GJ1214b. There's a planet that's going to be presented on Friday. I'm not going to spoil what it is, but I promise it's very interesting. There's HD209, and there might be some others that I'm not remembering. So yeah, if I were a betting man, I would say that this is an episodic outflow. Okay, so here's another oddball, TUI 1099b. This time, we're very sure that the orbit really is eccentric. And if you look at the mass, it's fairly low. But then if you look at the helium absorption signal, well, it seems like in the first transit, you see a 0.4% absorption. But in the second visit, in the main peak, you see negative absorption. Now, negative absorption is not physically possible. Right, so what's going on here? Well, remember I said the planet's orbit is eccentric. So the diagonal red lines indicating the wavelength of helium absorption should not be here. It should be, wait, what? Okay, good. It should be here. But it's also 1 sigma consistent with being here. So if it's here, then what we see is fairly easy to explain. Right, we're seeing helium absorption that's slightly blue shifted, as we see many times. It's consistent between the 2 visits. It's around 0.3, 0.4%, which incidentally is the weakest helium signal ever detected. Yeah, if that's the case, then what we see at 10833 angstroms is just stellar activity. Okay, so here are the mini Neptune helium detections in the context of all of the other escaping helium detections in the literature. I know I'm missing a few because this is not up to date. It's really hard to keep up to date given how fast the field is moving. But yeah, on the x-axis, we have the energy limited mass loss rate. On the y-axis, you have the observed mass loss rate. I say observed in big scare quotes because this is very order of magnitude. It's just proportional to the equivalent width of the helium signal. Here are the southern hemisphere targets. Here's a zoomed in version. And you see that even though in the whole population, you see this strong correlation between these 2 mass loss rates, when you go to just the mini Neptunes, you don't seem to see any correlation. So why is this the case? Well, I've just started on the modeling aspect of this project. But it at least seems that if you apply a 1D self-consistent radiation hydrodynamic model to these planets, you predict that the helium signal is far more sensitive to the metallicity than to the XUV flux. Right? So if you are run 100 times solar metallicity, the helium signals look pretty similar. And same for 200 times. Yeah, so the non-sensitivity to XUV flux is also a result of a recent paper by Allart et al. 2025. Maybe what's going on is that all of these planets have roughly similar metallicities, but a small variation in composition overwhelms even the much larger variation in XUV flux. Okay, so in the southern hemisphere, we see two normal helium signals. We see one potential episodic outflow, and we see a weak, highly blue shifted signal. If you have a model that you want to apply to this data, please contact me. That's partly why I came to this conference, to find collaborators who are good in theory. Yeah, I especially want to know how to explain the episodic outflow. Because if we're saying the helium signal is not very sensitive to the XUV flux, you can't explain it by invoking stellar activity cycles or stellar variability or something along those lines. Or at least it's much harder. Okay, any questions?
Great talk. Questions?
Okay, so I'm intrigued by the episodic variability. Of course, it could be that on your second night, you had more helium. If you had helium outflow continuously during your 6 hours a day, you would never know. Because you are building a spectrum out of transit and dividing it into the in-transit spectrum for difference. But actually, if you had a continuous annulus of helium, right, it wouldn't change. Okay.
Actually,
My question is, have you tried building an out-of-transit spectrum for another night, overcoming the difficulties of the shifting wavelength scale, and using that as your out-of-transit spectrum?
Yeah, good idea. So for this planet, I haven't tried. But actually, I don't agree that if you have a big annulus, you wouldn't see any variation. You will still see variation, right? Because the column density of the annulus is not constant. It's much, much higher in transit or when you're close to the planet than when you're very far from the planet. Yeah, WASP 121.
But I just mean, like, if you have an annulus of gas that's just orbiting with the planet.
Yeah, but
the column density changes.
So for WASP 121b, I think there are like big changes. Right, so JWST found that you have helium absorption across half the transit, right? But it's much stronger around the transit than at phase 0.25.
But I'm saying you don't need to have that.
Right. Yeah. Yeah. No, it's a good idea. I'll definitely try it. I'm kind of skeptical that it's going to work. Well, I'm skeptical that if you have an annulus, you'll have such a stable helium signal.
Okay. Thank you.
Hi, Andrea Caldiroli, ASU. So with respect to the XUV being less important than the metallicity, what is the range of XUV that you are applying in your models?
Yeah, so we can look at this. I say XUV is really the density scale XUV, which is the thing that determines the energy limited mass loss rate. And if we go one before, yeah, TOI 2540B, it's around 0.02 on this scale. And then TOI 1027B is around 1. So yeah, 1 to 2 orders of magnitude.
I guess I've got two questions for you. One, are there any plans to expand the survey to like other stellar types other than K-dwarfs? And second, is there a line, because I know that you're working with young segments for the most part, is it worth it or not worth it to look at maybe a little bit older, like is there a line there? What do you think?
Okay, so second question first. You can see that on this plot, I didn't just plot the planets that I showed in this talk. There's also a few that are not published. Well, okay, there are a few that are published. For example, TOI A36C, that's an older mini Neptune. It's maybe 2 gigayears, and you still see a relatively strong helium signal. Now, TOI 2134b at the very left, that's an even less active star. Yeah, so that one is actually fairly intuitive because you have an older star, low XUV flux and low helium signal. So yeah, we are expanding to older ages. And as for other stellar types, I do want to expand to M dwarfs. Now, there's not that many mini Neptunes around M dwarfs, especially around the later M dwarfs, but there are some. And I'm very curious what kind of helium signals they have. There are papers that predict 50% absorption, which seems extreme, but if we see that, that would be awesome.
We're running out of time, but please feel free to ask questions on Slack or at the breaks. Let's take our
virtual. Romain, if you can share your screen and mute.
Yes, can you hear me? Can you see the screen?
Yes. Right, so Allart is going to talk about a complex the orbit.
Sorry, I'm hearing a lot of noise. I don't know where it's coming from. Okay, it's good, perfect. So thank you very much. First of all, I'm really sorry to not be here today with you and for all the week. I had multiple things that happened along the way that not allows me to come here today. So yeah, I'm a postdoc fellow at the University of Montreal, and today I will speak about a new result we obtained with James Webb. But so first of all, can I switch slide? Okay, perfect. That's good. So just as a quick reminder, as we saw earlier today, we have multiple dozens of detections of helium escape going on, and you can see that are representing here in blue, and you can see their strength as function of their XUV flux. And most of these detections look similar to what we discovered in 2018 for ATP11b, which means that at high resolution, we have a transmission spectrum which is quite symmetric around the helium triplet position, helium lines, which is well resolved at high resolutions and for which you can measure the line profile. And in addition, from there, you can extract some kind of light curve as a function of time and see that the absorption is happening during transit and also symmetric. We have no clear pre or post-transit absorption, or at least this is the case for most of the targets. However, during the years, more and more targets have started to show some post-transit absorption and even some pre-transit absorption. This is the case, for example, for WASP-16NB, for which it was already speculated in 2018 by Lisa Northman, but recently with NIRPS, we gathered observations showing a very clear, repeatable transit absorption following the transit for up to 1 hour 30 minutes. And recently, with the James Webb Space Telescope, Vignesh Krishnas-Murphy obtained nearest source observations of WASP-107b, a well-known, well-studied exoplanets for atmospheric escape through the helium line. And he showed in his study that the helium light curve showed clear pre-transit absorptions and even post-transit absorption for a very long time. And in fact, we can ask the questions if for both cases, we really reach the baseline of no absorption from the planetary atmosphere. Have we observed enough before and after transit to be sure that we have observed the full absorption, the full escape from the helium line? And over the last 2 years, other results have shown that the helium outflow can extend much further than transit. The first one was obtained for ATP32 by Zhang et al. In 2023. And the second one was obtained by Gulli Santiago in 2023 for ATP67. These two planets have been observed with the same observatory, the HST HPF, so which is a ground-based telescope, which is a very a fixed window of observations. And so they have to compile multiple nights of observations over multiple months to gather these light curves and observe very long out-of-transit absorptions of helium. In the case of ATP32, it lasts for about 12 hours. And in the case of ATP67b, it's for about half of the orbital phase preceding the transit. And this is really curious and really strange, and at least compared to what we were expecting at first. However, recently, new study modeling led by Morgan McLeod in 2025 has shown that the planet's outflow of helium can be discriminated into two categories, from bubble-like atmosphere outflows to stream outflows. And so you can see here, for example, that the bubble outflow is what you can expect from what we know from Lyman alpha with like a cometary-like tail absorption. And some, in the opposite extreme case, in the stream case, you could even have a torus of helium outflow circling around the star on the planetary track. And so Morgan was able to show that we could try to put the different planets detected as function of their gravitational potential and its sphere to planetary radius to see if they are more likely to be in the bubble case at the bottom right or in the stream case at the top left. And so this is where we are currently about understanding how extended helium outflow can be. And so this leads me now to the study that I want to present you today, which is about James Webb NEAT observations of WASP.1b. So WASP.1b is a F-type star, quite young, about 1 giga-year-old. This age was obtained by David Singh using NIRSPEC data, and it is quite a fast-rotating star. The planet is the prototype of the ultra-hot Jupiter with a radius of 2 times the Jupiter radius, a bit more massive than Jupiter, on a very short period with 1.3 days. And also with a very high equilibrium temperature of about 2,400 kelvins. And it is also on a polar orbit. So WASP.1b was already known to have atmospheric escape from helium. It was obtained with Schreyer S+ from the ground, but it was only observed during transit. Here, the observations that we have are James Webb observations obtained with NIRISOS as part of the NEAT GTO program, which is led by David Lafreniere at the University of Montreal. It is a full phase curve containing 2 secondary eclipses and 1 transit for a total of 37 hours of consecutive monitoring of the star. And at the pixel of the helium triplet, we are more or less at a resolution of 600. So we are not sensitive to the spectral line shape of the helium triplet, but just at its temporal evolution and due to the high sensitivity of James Webb. And so here, you will see the standard maps you can have with time from mid-transit, with transit being in the middle, the first secondary eclipse at the bottom, and the second one at the top, as function of wavelengths, and the color will show you the excess of absorption. So we are starting at the first secondary eclipse with no absorption at all. The helium triplet will be around here, and you can start to see some excess absorption arising before transits that is really maximal during transit and last for a very, very long time after transit. And then we reach the second secondary eclipse where we have no absorption of helium. So this is a clear continuous absorption of helium that lasts for about 17 consecutive hours. And so you can put it like this in this excess helium light curve where you have on the x-axis the time from mid-transits and the absorption in the y-axis. In black, you can see the helium light curve for the pixel centered on the helium triplet. In blue, it's the pixel just on the left of the helium triplet, and in red, it's the pixel just on the right. The dashed curves are the best fit model we obtain, and that I will show you just after. And so what is really impressive to note here is that you have a strong absorption during transit, but which is preceded by a clear leading stream, but also a very strong trailing stream that lasts for a very long time. And you can see that they are both very stable for a very long time before dropping sharply at the start and at the end. And so from there, you can distinguish 3 different phases. What is happening during transit, what is happening before transit, which is the leading stream, and what is happening after transit, which is the trailing stream. And so we can compute transmission spectra for these 3 different regions, as you can see here. And you can see here what is happening, the transmission spectra before, during, and after transit. And what is important to note, in addition to have the increase of absorption during transit is the balance between the blue and the red pixel. You can see that the leading part, the line profile is quite symmetric, while it becomes more and more asymmetric toward the transit and after transit, which means that we are sensitive to some dynamic that we can model. And this model, it's a toy model because you don't have proper 3D models that are able to completely fit at the same time with spectral features and their duration and intensity. So we use the IF code developed in the Observatory of Geneva, and we transform it as a toy model to simulate, to reproduce our observations. And what we see, our basic model shows that we have a planet here with a clear leading stream that is going toward the star at high velocity and at low velocity, sorry, and a trailing stream that is going away from the star, pushed by stellar radiations, a bit like a cometary-like tail. And so this result really shows us how we have to rethink atmospheric escape and how we need to observe them. So as a reference in this plot, WASP.1b falls here. So it really follows this stream category that was proposed by Parke Loyd and suggests that helium outflows can be extended much further from the transits. Continuous phase curves are key to reveal these outflows because we don't know how many of our observations can be affected by such extended outflows. I mentioned this point. And so the key question that we need to ask ourselves during this workshop, but also on the long term, is how many planets have outflows extend far beyond transits? For how many planets have we underestimated the atmospheric escape and also the mass loss rate because we are just observing close to transit and we are missing this long stream pre and post transits that completely bias our knowledge of how much helium particles are escaping into space. And so we really need to rethink how we need to observe atmospheric escape. And I will leave you here on my conclusions and take any questions. Sorry.
Questions?
Hi, great talk and really cool observations. It seems to me that we've learned that we can't trust the baseline of helium observations. So I was wondering, why do you think that that line that you had as the baseline of the bigger transit is indeed a baseline? Is it like because it's not variable over a certain amount of time, or is there some metric you can say we're looking at the star with no gas in front of it?
So we cannot observe at different phases because we observe a full phase curve. So it will be difficult to know if there is more observations. If there is, it's not possible to get an observations where there is no outflow at all. So I agree with you that it's possible that we still are some kind of baseline here and we are really seeing a full torus of absorptions, but at least the absorptions on the 2 secondary eclipse are similar. So this gives us confidence that we are in some kind of at least similar regime, and that the pre-transit absorptions and the leading and trailing absorptions are reaching the same level. So does it mean we are reaching a continuous absorption of helium or just no absorption at all? I think it's difficult to tell for now. And maybe modeling can help on this, but I'm not even sure.
Yeah, great talk. So yeah, looking at this light curve, it seems like if you just ignore everything that's like very far out of transit, and just take a window that's a few hours before to a few hours after transit, you still infer a helium signal that's maybe 70% of the true signal, which doesn't seem that bad. Or do you think for other planets it will be worse, or like it will be about this bad for every planet?
So I agree with you that for WASP.1b, the detection reported by with Schreyer S+ by Saidel et al. This year was obtained for observations around this time window. So we are they were only looking at the absorptions from this, basically from this baseline to AER. So they are biasing their absorption by factor 2, which is quite huge for this kind of planets. So we do expect that this kind of extended streams and outflows should be prominent for ultra-hot Jupiters or hot Jupiters, but who can tell that, for example, WASP-107b, WASP-69b don't have such extended outflows? WASP-107b, we see that even the NIT observations, which is like 6 hours, is not long enough to really fully determine if we reach a baseline. And even if we reach some kind of baseline, have we reached the true baseline, which is like 10 hours before and after? It's difficult to say. So I think the only way forward is really to do phase curve with GEMSEP for all of these targets. And so we should ask for time for this and get time of attack on this. And we are trying to push for this now.
Let's take our speaker again. Speaker for the session is Morgan Saidel. He's going to talk to us about results from the first mass loss survey of F-type stars. F-star planet, sorry.
That's okay. It's a mouthful of a title. Great. Okay, so hi everyone. I'm Morgan Saidel. I'm a final year graduate student at Caltech, and I'm actually going to be building off a lot of what Romain just talked about for atmospheric escape on planets orbiting F-stars and talking about a survey that I had done recently to actually look at this process. So as we've heard throughout this workshop so far, atmospheric escape is a critical evolutionary process for exoplanets, and it's one we can actually observe with observations of metastable helium. And this is a really robust technique. So to illustrate this, I'm showing a plot here of confirmed exoplanets as these white-gray background circles, and then I'm showing robust detections of atmospheric escape using metastable helium as these different colored circles that you see here. And so far, there have been over 25 published detections of atmospheric escape in the literature, and the majority of these have been with metastable helium. So it's a really robust technique that has enabled some great science, as we heard both in Michael and Romain's talks. However, what I want you to take away from this plot is that overwhelmingly it's filled with orange circles. And that means that overwhelmingly our observations of atmospheric escape have been confined to planets orbiting cool stars like K and M stars. And that's been talked about briefly so far, but it's largely due to an observational bias. These stars emit proportionally more of their bolometric luminosity at X-ray and extreme UV wavelengths, which is needed to primarily create metastable helium. So earlier type planetary systems could have outflows, but detecting them with this tracer was just not expected. However, recently there were the first detections of atmospheric escape on planets orbiting early type stars like F stars, which I'm representing here with these blue points. And these were actually metastable helium outflow detections. And this was sort of a bizarre thing for me and others to see in the field because, as I mentioned, we thought that K stars were the primary stars for detecting this tracer. F stars emit a larger fraction of their bolometric luminosity at wavelengths that are actually going to ionize and destroy metastable helium. So we just didn't expect to see those outflows here. And perhaps what is even more interesting is that most of these new detections exhibit mass loss rates up to orders of magnitude faster than the typical mass loss rates we see in planets orbiting K stars, which I'm representing with this not to scale graphic here. So on the left, we have the typical mass loss rates we see in planets orbiting F stars, which are on the order of about 10 to the 12 to 10 to the 13 grams per second. On the right are the typical outflow strengths we see in planets orbiting K stars. For reference, some of those canonical systems are WASP-69 and WASP-107. And so those have mass loss rates on the order of about 10 to the 10 to 10 to the 11 grams per second. So the outflows on planets orbiting F stars appear to be much stronger. And as we heard in Romain's talk, they're also incredibly spatially extended. 3 of these systems have escaping planetary material that extends anywhere between 50 to 130 times the planet radius, which is much more extended than any outflows observed on planets orbiting K stars. And these detections become even more intriguing when combined with 2 new detections of atmospheric escape onto A-star planetary systems. Full disclosure, these are bomber line measurements and not metastable helium though. But what's really interesting about these detections is they're showing similarly strong mass loss rates. And so this was starting to show an interesting pattern, namely that planets orbiting early type stars were exhibiting some of the strongest outflows ever observed. but this is a very limited sample size. And so what we wanted to know is, are outflows categorically stronger on planets orbiting these hotter, earlier type stars? This would have major consequences for our interpretation of atmospheric survival on hot Neptunes and sub-Neptunes. And we also wanted to know what factors could be controlling the large outflows that we see. And so to answer this, we really need to start building up a population of these early type planetary systems with measured mass loss rates, which basically just means observing atmospheric escape in more of these systems. And so that's exactly what we did. We designed a ground-based survey to search for atmospheric escape on planets orbiting F-stars using Palomar Observatory. Palomar has an instrument called WORK, the Wide Field Infrared Camera, and that's equipped with an ultra-narrowband filter that's actually centered on the 1083 nanometer absorption feature of metastable helium. And that's actually a picture of the filter right there. And so this allows us to collect photometric metastable helium transits of our targets. And so we had 6 systems that we studied, and I actually have some results to share with you guys, which I'm excited about because I was weathered out on 12 out of 23 nights for this survey program. I've been working on it for 2 years. I think I have like the worst luck of any ground-based observer alive. But anyways, I finished the survey. I'm really excited about it. And what you're looking at is 5 transit observations with the date of each observation listed in the lower right. And we've got the name of the planet in the top left, along with the detection significance of each excess absorption. So the black points are bin data points. The blue line is the best fit model to the transit, but the depth is fixed to the nominal transit depth, whereas the red line is actually allowed to fit the depth that we observe with the metastable helium filter. And so if you're not familiar with this technique, I think it's kind of been mentioned before, but it's been a long workshop so far, and you might be jet lagged like me. But anyways, if you have an escaping atmosphere, that escaping gas is going to be absorbing or blocking more light. And so if you were to observe the transit of the planet in a bandpass that is sensitive to that absorbing escaping gas, then you should see a deeper transit. And so we do see deeper transits, or excess absorptions, as we like to call them. And you can think of the depth of each excess absorption as being roughly proportional to the mass loss rate. So on the right, we have 2 very strong outflows. On the left, 2 much weaker, more tentative outflows. And you might say a 2 sigma detection is not great, and I would agree with you, but it's informative to us because it's telling us it's not a strong outflow. We also had 2 non-detections for 2 systems, WASP 103 and KELT 7, which I'm showing here. Okay, so what do our initial results mean in the context of the previous literature measurements? Do we see similarly massive outflows, and can we explain what's going on? To understand what's going on, we need to compare our escape measurements to those in the literature. But how do we compare them? We can compare them by looking at factors we know are important for mass loss. One factor that is really important for atmospheric escape is the actual power for the outflow, or the X-ray and extreme UV radiation that the planet receives. This is what drives atmospheric heating and escape. So on one axis, we have the XV flux at the planet's orbit. Now, another factor that is really important for atmospheric escape is something I like to call Roche filling factor. This is the fraction of the planet's Roche lobe filled by the planet radius alone. So you can think of this as a factor that basically describes how likely it is the planet is undergoing Roche lobe overflow, or catastrophic atmospheric mass loss. And so if the planet radius is already filling a large fraction of its Roche lobe, put an atmosphere on top of that planet radius, it's very likely it's filling, if not surpassing, the Roche lobe and undergoing Roche lobe overflow. Now here are the literature detections of atmospheric escape in early type planetary systems, with their point size scaled to the published mass loss rates in these literature detections. For reference, the systems with the horizontal lines, those just represent systems we don't know the XUV fluxes for. So we're showing a range of possible XUV fluxes based on proxies that are close matches in effective temperature, stellar rotational velocity, etc. And so interestingly, all of these detections are clustered at high Roche filling factors. And so this was a hint that Roche lobe overflow definitely mattered in setting the strong mass loss rates for these systems. But to test if it really does matter, we wanted to look at things basically above and below the literature detections in terms of Roche filling factor. If Roche filling factor matters, we should see strong outflows above the literature detections and weak or no outflows below. And so now I'm showing some of the survey targets below the literature detections. For our survey targets, we saw non-detections, represented by the dashed circle for KELT 7, and then we saw weak or tentative detections for WASP 93 and HAPI 8, represented by the open circles with the closed lines. And the point size here is also proportional to the retrieved mass loss rates. And so at low Roche filling factors, we're seeing planets that are likely not undergoing Roche lobe overflow, and we saw very weak or no outflows at all. Now, above the literature detections, we saw a really strong detection for WASP-12b with a similarly strong mass loss rate to the cohort of literature detections. And so this was really kind of emphasizing that Roche lobe overflow definitely mattered in setting the strong mass loss rates for these systems, because we saw strong outflows at high Roche filling factors and weak or no outflows at low Roche filling factors. However, there's always a problem, and that's WASP-103. It doesn't fit this perfect picture because WASP-103 is at a really high Roche filling factor, and yet we saw nothing, no outflow, where we would have expected to see one. However, you'll notice this system is connected by that horizontal dashed line. This is one of the systems we don't have a published XCV flux measurement for, so we've adopted proxies here to encompass the possible range of XCV fluxes, but the actual XCV flux could be much lower. That would mean you'll have less power for the outflow and less ionizing radiation needed to create metastable helium, which could explain our non-detection. However, without this information, you're kind of in the dark for what's really going on. But this really suggests that XCV flux might be equally important in setting the strong mass loss rates for these systems. However, all of our planets are clustered at pretty similar XCV fluxes. What would be really nice is if we had a point that had a really high XCV flux and really low Roche filling factor. That would allow us to isolate the role of XCV flux on setting the observed outflow strengths for these systems. And we actually had such a planet, WASP-180ab. And this planet showed a comparably strong mass loss rate to WASP-12 and the literature detections. And so this really showed us that XCV flux is equally important in driving the strong outflows in these early type planetary systems. And so to kind of give a main takeaway for the survey and the talk, the outflows on planets orbiting early type stars exhibit some of the strongest mass loss rates ever observed. And these are powered by Roche lobe overflow and enhanced XCV fluxes in these stars. However, not all close-in gas giants orbiting early type stars have these strong outflows, evidenced by our non-detections and our tentative detections. So there's not some mechanism that's resulting in globally enhanced atmospheric escape for all early type planetary systems. And so I'll end with leaving up future directions for this survey program. If you're thinking, why should we still care about some of these early type planetary systems? A, they exhibit the strongest mass loss rates ever observed, and B, the most extended geometries. And I think that that could potentially affect the fate of some of these doomed worlds like WASP-12, which if you're interested in, you should come talk to me about. And we also want to get stellar XV spectra as well. And thank you. I will take any questions.
Questions?
Hi, Guangwei, Johns Hopkins. So can you go back a couple of slides to the beautiful chart? Yes, great. So can we like tentatively maybe draw a diagonal line, kind of like the cosmic shoreline, the FUV and the Roche lobe overflow? Say the top right corner is more likely and bottom left also.
I think you could if we knew the XCV fluxes for most of these systems. We don't for WASP-94, HAT-P67, WASP-93, and HAT-P8. So I think we need to get XCV fluxes for those to be able to determine a robust horizontal or diagonal line, but it is something interesting that's worth exploring.
Katie.
Thanks, Morgan. This is Kate Bennett from Johns Hopkins. This is really cool. I was wondering if all the literature non-detections around the M stars, the literature detections all have this really high mass loss rate compared to the literature detections on the M stars. Is there any chance that like there is equivalent, 10 to the 10 or 11 grams per second loss around F stars? Missing that, like, is there something in the F stars that would prohibit our ability to detect lower mass loss rates?
Yeah, that's a really good question. I think a lot of these non-detections are observational biases, like we're looking at helium lines, right? And helium might still not be a great tracer for some of these outflows, because if you do have a lot of NUV radiation, which F stars are known to emit, you're just going to destroy metastable helium, right? What would be interesting is looking at planets orbiting F stars and other lines, Balmer lines, H alpha, Lyman alpha, and seeing if you're continuing to see those strong outflows or even the weaker outflows that you're suggesting as well. Yeah, so that's something I'm interested in too.
Emily Pass, MIT. I was interested when you were showing the transits. It seemed like there's a lot of like correlated noise in the data, and I was wondering, is that stellar or is that observational, or if you could speak a little bit about those signals?
Yeah, no, that's a great question. Yeah, there definitely is. Unfortunately, for a lot of this program, the weather was just not super great, and so I think a lot of that correlated noise is just from bad nights of data. You know, when I was designing the survey, I had a lot of winter nights, and so winter is not great if you're a ground-based observer. You get a lot of clouds, a lot of, you know, water vapor in the atmosphere. But then there were also fires at Palomar, and that also complicated things, which we don't actually know how to deal with because it doesn't happen that often. So yeah, I think the biggest thing that's happening that I noticed a correlation between is weather.
Awesome survey, Morgan. I am curious, Parke Loyd, something about, so you mentioned A stars and F stars, and I think around like F4 is the craft break.
Yeah.
Where, so could you just talk about that in the context of your survey?
Yeah, totally. Yeah, so for our stars, 3 of them are above the craft break, 3 are below. There's actually no correlation, which when we initially designed the survey, we were looking at stellar rotational velocity, really high V sin I stars, really low V sin I stars, because we thought that could correlate with XeV flux. And at the time of the survey, there wasn't a lot of XeV published measurements. But there wasn't a trend really in the craft break sense. Like if you're looking just at effective temperature, WASP 93, which was a tentative detection, and then WASP 180 are above the craft break, but WASP 12 is below the craft break. So we're seeing detections and then non-detections or weak detections kind of all over the place. So there isn't a clear trend, but it was an interesting avenue that we wanted to explore, but it just didn't work out with anything. But great question.
Can I follow up real quick? Just to ask like how the XeV flux is measured.
Yeah, that's a great question. I think all of these are XMM Newton measurements. But what I didn't talk about is if you look at WASP 12 and Kelt 9, you'll see these little arrows, and those are upper limits. So they're not precise XeV flux measurements. And then obviously anything that's a horizontal line, we had to adopt a proxy. I mentioned those down there. So those were, I think, either Phoenix or, those were Phoenix proxies. Yeah.
We're running out of time, but feel free to ask questions in Slack. But let's thank Morgan and all the speakers.
All right, and next we're going to do some poster pops. So these are basically 1-minute advertisements for some of the posters that have been hung up. We had 6 people sign up for them. So I think the way we're going to do this is, I need my phone to time it, but if we could have the 6 people who signed up for the session 1 to come up here, we'll run right through here. So I have Froning, Falorca, Barat, Caldiroli, Leung, and Schreyer. Yeah, how about you? Lakeisha will be timekeeper with a loud alarm that'll go off. And first one on the list I have is Saugata. Just go past that. Let me do this. And your 1 minute starts now.
Okay. Hello, everyone. I'm Saugata. I'm a postdoc at MIT. I'm very excited about studying sub-Neptunes and particularly understanding their early evolution. And to do that, I study sub-Neptunes at the youngest stages, about 20 million years old, with JWST and HST, and compare them with their mature counterparts, which have evolved for billions of years. So please do visit my poster, and I'm interested in seeing how atmospheric composition evolves over time for these sub-Neptunes and how that affects atmospheric mass loss and vice versa. Thank you.
Thank you. Right, next I have Caldiroli. Am I pronouncing that right?
Caldiroli, yeah. It's difficult, yeah. Yeah, thank you, everyone. I'm Andrea Caldiroli. I come from University of Insubia in Como. So I come a long way today to share with you the results from work I've done in modeling the impact of flares on photoevaporation of primordial atmospheres. So basically, the main idea is that you have some quiescent irradiation from a star, you add up a contribution by flare. And what we have done using numerical simulation with the ATES code was try to understand the physics actually going behind this enhancement of photoevaporation. So we provided like analytic scalings for the enhancement of photoevaporation due to certain energy with the energy of flare. And we provided also a distribution proof that there is a certain energy, characteristic energy of flares, which is actually maximizing the mass loss enhancement. And putting this together in a very simple evolutionary model of the star, we proved that actually on the long time scales, flares are actually not important in the atmospheric extension of the planet. Thank you.
Awesome. Next I have Falorca. Oh, no.
Okay, thank you. Hi everyone, my name is Anselmo Falorca. I'm a second-year PhD student from Leiden University. My supervisor is Professor Leung Vidot. And over the last year, we have been developing a realistic model to help us study atmospheric escape from close-in exoplanets. So the model is as described, and it allows us to understand, for example, the case that I'm showing here. It's a hot Jupiter orbiting an old K-dwarf with a stellar wind sort of 2 times stronger than our own solar wind. We can see the hydrodynamical outputs on the left, so a 3D rendering of the results, but focus on the middle, which is a projection in the XY plane of the relative abundance of helium triplets. So it's these triplets that gives us the helium line. We then also developed a ray tracing model that would simulate how the hot Jupiter would transit in front of the star, which is displayed on the right. If you want to know how different stellar wind strengths change the results, please check out my poster. Thank you.
Awesome. Next I have Cynthia.
Hi, everybody. So I'm Cynthia Froning. I'm a staff scientist at Southwest Research Institute in Texas. And my poster today is about X-ray and UV observations of a young solar analog that we just obtained with Hubble and some archival XMM and Chandra data. This paper just went on AstroPH yesterday, so please check it out if you have a chance. We used the comparison of the 17-million-year-old solar analog to the present-day sun to estimate the excess XUV emission in the system. And we also derived a scaling relationship then between EUV emission expected as a function of the age of a solar-like star against age. And that was, in my case, was scaled against Lyman alpha predictions for the EUV component. Kevin France will show you a little bit more tomorrow about some of the other ways that we try to estimate the unobservable XUV flux. But the other thing I want to mention is that we saw that we were unable to successfully reconstruct Lyman alpha in the system, and we believe that's because there's some internal absorption, high velocity material that's absorbing Lyman alpha that could be potential evidence for an outflow, and we'll be looking for that with Hubble next year. Thank you.
Right, next I have Ethan Schreyer.
Hi everyone, I'm Ethan, postdoc at UCSC, and my poster is about situations which have been talked a lot about today actually, which is when extreme mass loss could lead to the formation of a torus of gas. And there may be signatures of this just in the absorption spectrum of the star, but it's not always obvious that you're going to be able to tease those out by just looking at kind of a simple spectrum. And so my kind of aim is to investigate how to use complementary observations of stars out of transit and kind of compare the properties that you see to kind of normal main sequence stars and see if you get very unusual properties. And this kind of is evidence of circumstellar gas. Yeah, that's it.
Right, last but not least, Matthew Leung talking to us about Viper.
Hi, I'm Matthew Leung. I'm a PhD student at Harvard working with Dave Charbonneau, and I'm excited to share about a new high-resolution spectrograph we're developing called Viper, which is specifically designed for helium escape observations. So what we're really interested in doing with this resolving power of 300,000 is taking spectra throughout the entire full orbital phase in order to map out the 3D velocity structure of escaping gas. And what's cool about Viper is that unlike conventional high-resolution spectrographs, we're using a relatively new dispersive element called the VIPA, which has higher dispersion, higher throughput, has a smaller form factor, and much lower cost. And this is a very exciting project. We're in the process of finalizing the optical design, and we hope to have it on sky in 2027 on a 1.5 meter class telescope. If you're interested in learning more about this, please check out my paper and come find me. We're open to collaborations. Thank you.
All right, great. So those are the poster pops for this session. There's a few other posters there too. They'll be up the rest of the day today, the rest of the day tomorrow. Tomorrow afternoon, I believe we have a dedicated poster session, which hopefully we can all go around and take a look at all these posters. And then there'll be a whole new batch of posters on Thursday and Friday with another round of poster pops on Thursday morning. So encourage you to track them down if you found any of these interesting and have them tell you about their poster. But yeah, more on the poster session tomorrow. But now I think we have time for a break. So I'll see you all back here at 3:45. Thanks, guys.